I will be going over the 2005 number 4 free response question, specifically on the topic of Euler's method. Part A says, on the axis provided, sketch a slope field for the given differential equation at the 12 points indicated, and sketch the solution curve that passes through point 0, 1. So they give us a differential equation, dy over dx is 2x minus y. And to sketch the slope field, you just plug in the values of x and y at each point into this formula. So negative 1, 0, that would give you negative 2 minus 0, which is negative 2. So you draw a small line with a slope of negative 2, and you go doing that for every single point that the question provides. And you're going to draw this in a booklet that the test will provide, and the next part says to sketch the solution curve that passes through point 0, 1. So you plug it in here, you get negative 1 as your slope. So you have negative 1 here. And looking at the slope field you have, you can see the general trend of how the curve will form if you were to draw a line. So this is just how you sketch the solution curve that passes through point 0, 1. In part A, you have the possibility of 3 points. The first point is for having the zero slopes, which is here and here, and the non-zero slopes, everything else. And the third point comes from the curve that you draw through 0, 1, and it has to be accurate. Part B says the solution curve that passes through the point 0, 1 has a local minimum at x equals the natural log of 3 over 2. What is the y-coordinate of this local minimum? So because it's a local minimum, we know that the slope is going to be 0. And so we have the differential equation dy over dx equals 2x minus y. So we set dy over dx equal to 0. And if we plug 0 in for here, we have 0 equals 2x minus y. And then you get 2x equals y. So now all you need to do is plug in the natural log of 3 over 2 for your x to find the y coordinate. So y equals 2 times x, natural log of 3 over 2, and that's y coordinate equals 2 times natural log of 3 over 2. And you can get 2 points for part B, and the first point comes from setting dy over dx equal to 0, again because it is at a local minimum. And you get the second point for the correct answer, for the y coordinate. Part C says, let y equals f of x be the particular solution to the given differential equation with the initial condition f of 0 equals 1. Use Euler's method starting at x equals 0 with 2 steps of equal size to approximate f of negative 0.4. So again, we use the differential equation dy over dx equals 2x minus y. And at f of 0 equals 1, we have a slope of negative 1. And we get that again just by plugging in 0 for x and 1 for y. So now that we have a point and a slope, we can make an equation. So y minus 1 equals negative 1 times x minus 0. Once we have this equation, we plug in the x value for the first step. And because we want 2 steps of equal size, and it starts at x equals 0 and ends at negative 0.4, we know the first step is going to be negative 0.2. So we plug in negative 0.2 into this equation, and you solve for y. And your f of negative 0.2 is going to come out to be 1.2. And then using the point negative 0.2, 1.2, we calculate the slope at this point. And that's again using the differential equation. And so you'll get negative 1.6. Now onto the second step, we create another equation with the point and the slope. So you get y minus 1.2 equals negative 1.6 times x minus negative 0.2, or x plus 0.2. And again, we plug in negative 0.4. And when you solve for f of negative 0.4, you get 1.52. So you can get 2 points for this part. The first point comes from accurately having the Euler's method with the 2 steps, so showing these steps. And then the second point is the correct approximation for f of negative 0.4, which is 1.52. So part D says find d2y over dx squared in terms of x and y, and determine whether the approximation found in part C is less than or greater than f of negative 0.4. So we use the differential equation, and we find the derivative to find this. So we have 2 minus y prime, because we are in terms of x. And when you have y prime, you just want to plug back in the first equation, because y prime equals 2x minus y. So you'll have 2 minus 2x minus y, or 2 minus 2x plus y. Now based on this equation, we know that the derivative of dy over dx is always going to be positive in quadrant 2, because x is always less than 0 and y is greater than 0. Any values that you plug in into here, you will get a positive number because there's a negative in front of the 2x, and it's positive y. So because it's positive, you know that it is concave up. And because it's concave up, you know that 1.52, which is the approximation found in part C, is going to be less than the actual value for f of negative 0.4. Because tangent lines, we use tangent lines to find the approximation, and their slope is always going to be lower than the actual concave up. So if we have to demonstrate, we have a concave up graph. And when we're doing approximations using tangent lines, which is Euler's method, we're going to have tangent lines like this, and then tangent lines like this. So they're always going to be less than the actual value. And so you can get 2 points for this part. The first point comes from accurately solving for d2y over dx squared, and the second point comes from coming up with the correct answer with the reason, which is right here. So some common mistakes that people can make when solving this kind of problem is that when doing Euler's method with steps, oftentimes people forget to calculate the new slopes. So the initial condition was f of 0 is equal to 1, and you know that the slope is negative 1. And when you're doing the next steps, for example, when you get f of negative 0.2, when you write the equation for that, you want to calculate the new slope at that point. You don't want to be using negative 1 again. And the second thing to note is that to remember to plug in dy over dx back in when you're solving for d2y over dx squared, because oftentimes when you're solving for this, you will get y prime back because you'll be solving in terms of x. And so, for example, in our problem, we had 2 minus dy over dx. You're just going to plug back in dy over dx that they have given you into the equation.